Origin of magnetic fields. As stated earlier, when a magnet is cut in half, and those pieces are cut in half, and this is continued all the way down to the atomic level, each piece will still have a north and south pole. The real explanation requires an understanding of quantum mechanics, but we can use some classical concepts to give you a working understanding of this phenomenon. In 1819, while searching for a relationship between electricity and magnetism, Hans Christian Ørsted set up a current-carrying wire above a magnetized needle, as seen in the drawing below, from a text by Augustin Privat Deschanel in 1876. When there was no current in the wire, the needle aligned with the magnetic field of the Earth and pointed north. When current was supplied, the magnetized needle rotated on the pivot and pointed at a right angle to the electric wire. The direction of this rotation would depend on the direction of the current. This is easy to recreate in the classroom. If you connect a wire to a battery and then place it on top of a compass, the compass needle will deflect away from Earth's magnetic field and will instead line up with the magnetic field created by the current in the wire. Ørsted deduced that electric current produced a magnetic field that affected the compass needle more strongly than the Earth's magnetic field. The below pictures show current-carrying wires generating magnetic fields that deflect compass needles. With no current, shown here, the compass needles all point north. When the current is turned on, the compass needles point in the direction of a circle around the wire. Remember this slide from earlier? It stated that the Earth's magnetic field is caused by the circulation of molten alloys in the Earth's outer core. Picture the molten alloys as having many free electrons that move together, and you have a current, which is what Ørsted demonstrated. Currents create magnetic fields. Classically, the Bohr model of the atom shows electrons orbiting the nucleus. As previously mentioned, current, which is made of moving charges, generates a magnetic field. Therefore, since electrons are charges that are moving around their atoms, they generate magnetic fields. Most of these magnetic fields generated by electron movements cancel out. However, sometimes there will be a non-zero net magnetic field. In order to demonstrate the creation of a magnetic field, the picture indicates the electrons moving in orbits. This is not to scale and is not the current quantum mechanics view of the atom. Another contribution to the magnetic field of the atom is a thing called electron spin. Since the electron is a point particle, it really isn't spinning at all. This is an effect explained by quantum electrodynamics. This spin factor adds to the strength of the magnetic field created by the orbital motion of the electrons. Again, this picture is not to scale, it's just used to demonstrate the electron spin as the electron is orbiting the nucleus. A magnetic dipole is simply a very tiny magnet. Remember when we cut a magnet in half and then we had two magnets? You could cut those in half and so on until you got down to the atomic level. Some atoms have electron configurations that cause them to be magnetic dipoles. Electrons orbiting a nucleus and spinning on their axes constitute moving charges and therefore create magnetic fields. The sum of these effects may cancel out, creating no net magnetic field. However, if the effects do not fully cancel out, these atoms are permanent magnetic dipoles. The magnetic dipole moment of a magnet or an atom or electron is pointed in the direction of the north pole of the object and represents the strength of the magnetic field produced by the object. It is a vector that represents how strongly the dipole will interact with an external magnetic field. Using the Bohr model, we have an electron here traveling clockwise, which means we have a current going counterclockwise. Remember, conventional current is opposite electron flow. The vector shown to the left represents the direction and strength of the magnetic dipole moment due to the electron movements. The arrows in the below diagrams represent atoms and their magnetic fields, with the arrowhead the North Pole and the other end the South Pole. So these show their magnetic dipole moments. Each group of like-pointed arrows is called a magnetic domain. In a magnetic domain, each atom has its magnetic moment in the same direction. So here's a domain, there's a domain. What do you think is happening below? Which picture could be a permanent magnet? Which could be a piece of plastic? For a random group of atoms, there's no real reason for their magnetic poles to align. The picture on the left shows a pretty random ordering of magnetic field directions, with aligned fields only in each magnetic domain. Looking at the left picture as a whole, the various magnetic fields cancel out, so it would not be a very good magnet in this state. It could be a piece of plastic or a certain type of metal that could become a magnet with the application of an external magnetic field. As you move from left to right, more of the magnetic field lines are in the same direction. The middle picture shows a large domain in the middle where the field arrows are all pointing up. Finally, in the third picture, all of the field lines point up in the same direction and can be visualized as a bar magnet with the North Pole up here and the South Pole down here. When an external magnetic field is applied to materials, they respond in three ways. Ferromagnetic materials can be permanently magnetized by the application of the field. All of their domains will line up in the same direction. Examples include iron, nickel, and cobalt. Paramagnetic materials weakly interact with the external field and temporarily line up some of their domains so they're attracted to magnets. When the field is removed, the domains resume their random ordering. Examples include magnesium and lithium. Diamagnetic is another weak temporary effect, but in this case, the domains line up opposite the external field, so these materials are repelled by a magnet. Examples include mercury and bismuth. Paper clips are typically made of steel, which is mainly composed of iron, a ferromagnetic material. When in the presence of an external magnetic field, in the case below, this bar magnet, the magnetic domains in the paper clips align, and each paper clip becomes a small magnet. If you were to zoom in on the metal in the paper clip to the right, here is what it would look like with no bar magnet nearby. All the domains would be in random orders. But as soon as you put the bar magnet here, then the domains are all going to point in roughly the same direction. This one's not. They don't necessarily all point in the same direction. But as a whole, the paperclip becomes a magnet with the north end attracted to the south end of this bar magnet. You use a bar magnet to pick up one iron paperclip. You then move the magnet and paperclip combination over a group of paperclips, and they get pulled up until you have a chain of clips. You then try the same experiment with a group of thin copper wires. None of them move. Explain why the iron paperclips were attracted to the magnet and each other, and why the copper wires were unaffected. Iron is ferromagnetic, so its domains will line up with the applied external field of the magnet. Each iron paperclip will have its north pole pointed in the same direction, so they become a chain of little bar magnets and are attracted to each other. The effect, in this case, is not permanent, and after the magnet is removed, the domains will fall out of alignment. Copper is paramagnetic, and its domains will not line up enough to be attracted to the magnet.